All right, our second equation for today is definitely a little bit more involved, a little bit more complex than the first one. So the thing that makes this probably a lot trickier than the first one we did in this series was this problem's got a cosine and a sine in it. And really, when you have a trigonometric equation, you want to try to just use one of our ratios. And so that's where we're going to be using one of the identities, probably from our formula booklet. In this case, I'm going to be using this cosine squared plus sine squared equals 1. And so what I want to do is I want to get that cosine squared by itself. So I'm going to manipulate this a little bit by taking sine squared theta off of both sides. So minusing sine squared theta. That's going to cancel those out. And so I've kind of created a new identity, and the new identity is cosine squared theta is equal to 1 minus sine squared theta. It's not really a new identity, it's just taking that one that's given to us and manipulating it a little bit. The reason I did that is now in my equation, that cosine squared x, I can replace it with 1 minus sine squared x. So let me do that. Negative 2, now instead of cosine squared, I'm going to write 1 minus sine squared. And now I've created an equation that's equivalent, but everything is in terms of sine. Okay, so let's do a little bit of simplifying. I'm going to distribute that negative 2 into my brackets. So negative 2 plus 2 sine squared x minus sine x plus 1 is 0. I can put my constants together, negative 2 and 1. So that's 2 sine squared x minus sine x minus 1 equals 0. And at this point, I'm dealing with a quadratic here. Some people, and this is optional, it kind of depends your preference. Some people like to say, okay, I'm going to make sine x just equal to kind of a dummy variable. And the reason they do that, sometimes it's a little bit easier to see the steps. So I could rewrite this problem as 2a squared minus a minus 1 is equal to 0. And I'm going to solve for a. Now, I'm going to have to bring sine x back in later in the problem, but this might make the solving a little bit easier. You could use the quadratic formula here. Personally, I think factoring it is a much more efficient strategy. I know the first two terms in those binomials have to be 2a and a because 2a times a gives me 2a squared. That's the only combination that's going to work. And so I know that, and then the last two numbers have to be 1 and 1, because 1 times 1 is the only thing that will give me 1. Then I just have to think, all right, what are my signs going to be? And you could just kind of guess and check if you wanted, or, the more you do this, the better you're going to get. Turns out that needs to be a minus, and that needs to be a plus. The reason that it's that particular combination is I'm trying to make a negative a in that middle term. And if I multiply the 2 in the middle, that gives me a positive 1a. And I multiply the 2 on the outside, it gives me a minus 2a. And plus 1a minus 2a gives me that negative a value that I'm looking for. So that's what this would factor down to. Let's go ahead and erase that so we got a little bit more room to work with here. All right, so what's a going to be? Well, what makes 2a plus 1 equal to 0? If I went through and solved that, a would have to be negative 1/2. And what makes a minus 1 equal to 0? Well, it's when a is equal to 1. Great. So I've solved for a, but that's not what this question's asking. The question's asking you to solve for x. So now I need to bring this sine x back into the problem. So I'm going to write that as sine of x is equal to negative 1/2. Over here, sine of x is equal to 1. Okay, now these are kind of like the first problem that we did in this series. I'm going to start with this, the sine of x is equal to 1, because that one's, I think, a little easier to solve. And I'm going to go back to my unit circle. Always goes back to the unit circle. Remember, the definition of sine is the y-coordinates on the unit circle when I draw my angle. There's only one coordinate. There's only one point that has a y-coordinate of 1, and that is right up here at the top, okay, at 0, 1. All right, so what angle would intersect at that point? It's got to be the angle that goes straight up. So it's this angle right here, which is 90 degrees, or in this problem, the domain is given to you from 0 to 4 pi. So that means that we're going to be working in radians. So rather than saying that x is equal to 90 degrees, which it is, we would be expressing this in radians. And so x would equal pi over 2 radians. Okay? But keep in mind, the domain goes all the way up to 4 pi. So I could also, on this one, instead of just stopping right there, I could do another full rotation. Like I could rotate one full rotation and get back to that same point. And so that angle right there is, I would have pi over 2, but then I would add another rotation or another 2 pi radians onto that. If I did that, pi over 2 plus, I need a common denominator. Some of you could just do this in your head, which is fine too. Okay, but 5 pi over 2 would give me a second solution. So both of these values for x are going to make the second part of that quadratic equation equal to 0. So great, I've got some of my solutions. What about the other part? The sine of x is equal to -1/2. This is where you really have to know your unit circle and you have to know your special right triangles and all of that sort of stuff. So when you see that 1/2, that should be a clue that, oh, maybe I'm going to be using my special right triangles. Okay? And if you think back, like what angle, when you take the sine of it equals 1/2. Now I've got it drawn out to illustrate this, okay? Over here is my special right triangle that uses, well, I said 30, 60, 90, or 30 is pi over 6, 60 is pi over 3. So you're going to want to think about radians here. So the sine of what is equal to 1/2? Well, that would be pi over 6 because the opposite over the hypotenuse, opposite's 1, hypotenuse is 2. So that tells me that the sine of pi over 6 is equal to 1/2, which is great, but remember what I'm trying to make on this problem. The question's asking the sine of x is equal to, when is the sine of x equal to -1/2? So this is where you have to then think about your unit circle. Where is the sign negative? Or in other words, where are the y values on the unit circle negative? The y values are negative everywhere below the x-axis. And if I go back and look at my unit circle, well, that would be everything down here. Okay, so where does that happen? Well, it happens right here. Let me highlight these. I'll switch the color in blue. So here it's equal to -1/2, and over here the y value is equal to -1/2. So what are those angles going to be? Well, it's going to be 180, and then I need to go a little bit more to get to that line. Well, how much is that? That's the pi over 6. So it would be pi plus pi over 6, and that's where I get my 7 pi over 6 from. So that angle, 7 pi over 6, is going to equal -1/2. Great, let's go add that. Erase this stuff right here. So one of my values for x is going to be 7 pi over 6, okay? But remember, this is going all the way up to 4 pi, so I don't have to stop right there. I could do another full rotation. I could do there, and then I could go around again. Okay, so I could add another 2 pi onto that 7 pi over 6. And what's that going to give me? Let's see here, 7 pi over 6 plus 2 pi. Now, I could just write 2 pi, but in order to add these, I need a common denominator. So the equivalent thing to 2 pi would be 12 pi over 6. I could add those, and that would give me 19 pi over 6. So that would be another solution. So x is 7 pi over 6 and 19 pi over 6. We're not done yet, because where else on the unit circle is the y value -1/2? It's not just in the third quadrant, but that's also true in the fourth quadrant. So over here at this point is also going to be another solution. Let me erase some of these lines so it doesn't get too confusing. Get rid of all this stuff. And so another possible solution is, in order to make, let's draw the line here, to that angle. Okay, you can see on the unit circle it's 11 pi over 6, but the way you would calculate that is it's that rotation right over there. Remember, this angle, okay, going back to our special right triangles, is pi over 6. So you could just try to memorize everything in the unit circle, or you could think, how could I get that value right there? Well, I could take 2 pi minus pi over 6, okay? That would be 12 pi over 6 minus pi over 6, and that gives me 11 pi over 6, which is right there on the unit circle. So that would be another solution. Let's add that to my list. 11 pi over 6. Am I done yet? Of course not. There's still one more, because remember, it goes all the way up to 0 pi. So I could keep this going, okay, and I could rotate around another 2 pi. So I would have to take that 11 pi over 6 and add another 2 pi to that. And 2 pi I would write as 12 pi over 6. So I have a common denominator, which gives me 23 pi over 6. Okay, almost to 4 pi, but not quite. So that would be my final solution, okay? 23 pi over 6. So this problem, I told you, was a little more complicated, okay? Would have a total of 6 solutions. All right.